We learned already that electrons are negatively charged subatomic particles. And we also talked about how the electrons are found in clouds around the nucleus. You've probably seen lots of symbols for atoms, something like this, where the electrons are represented as having specific orbits. What actually is the real case is that the electron cloud is a prediction of the area in which the electrons can be found. So if we have our nucleus here in the middle, and if we think about this circle here as being a three-dimensional sphere around the nucleus, we can say that at any given time, if I was to take a snapshot of this atom, that the electron would be found somewhere in this sphere or this cloud around the nucleus. But I couldn't be sure exactly where it is. It might be here, it might be here. And if I was to take different photos at different times, the electron would be in an unpredictable, non-random place somewhere in that cloud. So the electron cloud is just giving us a prediction of the area in which the electrons can be found. There's also energy associated with the electron clouds. So the electron clouds, they're also known as electron shells, and they're also known as energy levels. Let's just make a representation in 2D of an atom. And if we have our nucleus here, I can draw one energy level like this, and I can put an electron here. Now, think about subatomic particles in terms of their charge, right? Now, the electron has a negative charge, and the protons in the nucleus have a positive charge. So negative and positive things attract each other, right? If I had two powerful magnets here, and one end has a positive charge here, and one end has a negative charge, they're going to want to move together. Now, the fact that it's orbiting out here outside of the nucleus, that it's found out here away from the positive charge, means that it's moved away. It's moved farther away than that charge would probably prefer to be. If I was to take this, this negative magnet now and move it across the table, so now my negative magnet is over here and my positive magnet is over here. If these are really, really powerful magnets, I'm going to have to exert some force to be able to hold this negative magnet away from the positive one. Otherwise, it's going to rapidly move towards that positive magnet. So what I've created here now is something called potential energy. By moving this magnet away, I've created a scenario where the magnet wants to move. It wants to release this potential energy as kinetic energy, or it wants to move towards the positive magnet. So now when I have my nucleus and I think about it in terms of these energy levels, we think about it in terms of energy levels because it took energy to have this electron out here at this orbital. So there's some sort of energy associated with this energy level. And if I have multiple energy levels, I'm going to have even more energy associated with this second energy level. So as I move out in energy levels away from the nucleus, the electrons that occupy these energy levels have more and more energy because they've been pulled farther and farther away from this nucleus. So if I was to talk about energy levels in terms of, say, the first energy level or the second energy level or the third energy level, there is more energy associated with energy levels as they increase in number. So energy is increasing as we increase the number of the energy levels. We can also talk about the energy levels in terms of the number of electrons that can occupy those levels. And I'll draw my first energy level. And it's referred to as 1s. So 1 for the number of the energy level. And the letter that's associated with the number is basically just defining the shape of the electron cloud. So it's not going to be important for our purposes to actually know what all the shapes are, but just be aware that that's what this is describing. So each kind of an orbital has a different shape. An s orbital has a specific kind of a shape. And in a moment, we'll talk about a p orbital, which has yet another kind of shape. Each orbital surrounding the nucleus can be occupied by 2 electrons. So let's draw our nucleus again, and I'll draw orbital 1. I can have an electron here, and I can have an electron here. Right? So this would be a full orbital. Right? And if I then go out to the second energy level, the second energy level is actually defined by 2s and then 3 kinds of 2p's for a total of 8 electrons. And just remember that this is a representation of an atom. But this is just for us to understand how many electrons we're talking about when we want to talk about atoms and how they interact with other atoms. And it's important to be able to represent the electrons because the electrons are going to define the reactivity of an atom with other atoms. And we talk about the electrons in the outermost shell. So in this case, let's say I have 1 electron shell and I have 1 electron in this orbital. This electron level is called the valence electron level. And the electrons in this orbital are the ones that are going to interact with other atoms. Now, atoms want to have full electron shells. So we talked about 1s as being able to hold 2 electrons. So this atom with only 1 electron in this valence level is unstable. And it wants to have a full valence level. Take another example here. If there's 2 electron levels here, if I had 1 electron out here in the second level, this valence level has 1 electron, right? So if I added another electron, that's not going to help me because at the second energy level, I want to have 8 electrons. So I would need to add 7 other electrons to fill this valence level. But I could also just remove this electron and end up with 2 electrons in this 1s level here. And that then would be more stable because this second electron level has been emptied. If we take a look again at the periodic table, we can now see how the organization of the periodic table is going to help us predict the reactivity of various kinds of atoms. So generally speaking, in biology, we're going to talk about the first, second, and the 13th through 18th columns here. And what you can see here is that the first, second, and then these other columns 3, 4, 5, 6, 7, and 8 are sometimes referred to as groups 1 to 8, signifying atoms that have 1 through 8 valence electrons. And all of the atoms are aspiring to be like the atoms in this 8th column because all of these atoms have 8 valence electrons and are most stable. And these atoms are referred to as noble gases. So we've learned a lot about electrons in this lesson. We've learned that the electron shell defines a space around the nucleus where the electrons are most likely to be found. We've also learned that this can be referred to as an energy level. And we've also learned that the electrons in the outermost energy level are referred to as valence electrons. And finally, we've learned a little bit about the organization of the atoms in the elements in the periodic table and how the atoms without a complete valence shell aspire to be more like the noble gases, which have a full valence level.